Hello everyone, welcome back to my YouTube channel. Myself Sai Vaishnavi began studying in Sri Venkateshwara College of Engineering in Department of Electronics and Communication Engineering. Semester is second semester, subject is Applied Physics for Triple E stream, topic is about characteristics of lasers. Laser's full form is light amplification by stimulated emission of radiation. It has two mirrors, one side 100% reflective mirror and the other side is 99% reflective mirror. Now let's see the definition of lasers. Laser, a device that stimulates atoms or molecules to emit light at particular wavelengths and amplifies that light, typically producing a very narrow beam of radiation. The emission generally covers an extremely limited range of visible infrared or ultraviolet wavelengths. Characteristics of lasers: directionality, high intensity, monochromacity, and high degree of coherence. Let's see directionality. Laser emits light which is highly directional. Laser light is emitted like a relatively narrow beam in an exact direction. Ordinary light as light coming through the sun, a light bulb or a candle is emitted in several directions away through the source. The degree of directionality is expressed into terms of divergence. The divergence tells how quickly the beam spreads while this is emitted through the laser. The angle of divergence can be expressed into degrees as given below. Pi equals to a2 minus a1 divided by 2 into d2 minus d1. Here d1 and d2 are the distances through the laser window to the two spots and a1 and a2 are the diameter of the spots. Now let's see high intensity. High intensity lasers, free electrons and the generation of X-rays from solid density plasmas. The laser produced 50 millijoule 180 femtosecond pulses at 5 Hz. This translates to a maximum intensity. At such high fields, the AC stark shifts of atoms placed at the focus is much greater than the ionization energy. The characteristics of multiphoton ionization of atoms in intense laser fields was studied by angle resolved photoelectron spectroscopy. Free electrons placed in high intensity laser fields lead to the harmonic generation. This phenomenon of nonlinear compound scattering was theoretically investigated. Also, when these high intensity pulses are focused on solids, a hot plasma is created. This plasma is a bright source of a short X-ray pulse. The pulse width of X-rays from these solid density plasmas was measured by time-resolved X-ray spectroscopy. Now let's see monochromaticity. We know that the wavelength and therefore a frequency of a light wave is related to the color that we perceive. A light wave with a single wavelength has a single color. It is monochromatic. All of the harmonic electromagnetic waves we have been writing so far are monochromatic because they have a single frequency and wavelength. But no light wave in the real world is ever purely monochromatic. While light sources such as light bulbs are designed to emit many wavelengths of light, as we generally find this broad spectrum light more enjoyable, we evolved to make use of sunlight, which has a very broad spectrum of wavelengths. Laser light has a much narrower spectrum of wavelengths than a light bulb. But even laser light can't be purely monochromatic. An ideal monochromatic wave would have to persist for all time because even turning the light beam on and off introduces more frequency components. Non-monochromatic light can be written as a sum or superposition of monochromatic light waves. Mathematically, we call this Fourier analysis. Fourier series are sums of time harmonic functions which can represent any periodic function. Fourier transforms are integrals over time harmonic functions which can represent any arbitrary function. And the last one is high degree of coherence. Coherence expresses the potential for two waves to interfere. Two monochromatic beams from a single source always interfere. Physical sources are not strictly monochromatic. They may be partly coherent. Beams from different sources are mutually incoherent. When interfering, two waves add together to create a wave of greater amplitude than either one, constructive interference, or subtract from each other to create a wave of minima which may be zero destructive interference. Depending on the relative phase, constructive or destructive interference are limit cases, and two waves always interfere even if the result of the addition is complicated or not remarkable. Two waves with constant relative phase will be coherent. The amount of coherence can readily be measured by the interference visibility, which looks at the size of interference springs relative to the input waves. As the phase offset is varied, a precise mathematical definition of the degree of coherence is given by means of correlation functions. More generally, coherence describes the statistical similarity of a field, electromagnetic field, quantum wave packet at two points in space or time. Thank you for watching my video. If you like this video, please like, share and subscribe to my YouTube channel.